This is my lab report for Lab 1, constant velocity. The purpose of this lab is to investigate one-dimensional motion at constant velocity. In the formula form, Newton's second law is commonly written as F equals ma, which means the net force acting on an object equals its mass times its acceleration. A simple rearrangement is possible, and now, Newton's second law states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass, which is the definition more applicable to our purpose because constant velocity occurs when the net force is zero and thus no acceleration is present. So, how will we investigate Newton's second law? First, we will collect real-world position and time data from a video of an object moving in a straight line. Then we will use Tracker to analyze the motion quantitatively, and we will then develop a computational model based on Newton's second law with zero net force to represent the motion, and finally we'll compare experimental observations with model predictions to test the validity of the assumption of constant velocity and zero net force. My results confirm Newton's second law predictions by showing that the object moved with constant velocity as both the experimental data and computational model produced nearly linear position versus time plots. I had to make a few key assumptions during this experiment. For starters, I had to assume one-dimensional motion, so we're ignoring any motion that wasn't in the x direction. Next, friction, air resistance, and other external forces are assumed to be negligible, so they don't affect the constant speed motion. Lastly, we have to assume that the calibration stick provides an accurate scale for converting video pixels to real-world distances. We utilized the meter stick in our video to ensure as much accuracy as possible here. Tracker was used to track and analyze the motion of an expo marker rolled across the table. This event can be seen in this video. Take note that the system is the object whose motion is being tracked. In this experiment, that is the expo marker. The surroundings is everything outside the system that can interact with it, including the air, the surface the object moves on, the tracker equipment, and any external forces. However, as I previously mentioned, we are assuming external forces to be negligible. GlowScript was used to construct the computational model. GlowScript is a programming environment, so I had to turn our physics principles into code. Since we want to model constant velocity, I started by making the net force equal to 0. Next, we can rearrange the velocity update formula based on Newton's second law, and since the net force is 0, the final velocity is essentially equal to the initial velocity. Lastly, I had to update the position to ensure that the object wasn't stationary, so I used the position update formula to continuously add the velocity multiplied by the time step. This allowed the object in my model to keep moving at the same speed. For my initial conditions, I measured the expo's marker's mass to be 0.016 kilograms. I used my tracker data to find the initial position of the expo marker in my video, and I used the equation where velocity is equal to the change in position over the change in time to determine my initial velocity. I took the first two data points in my tracker data for the calculation shown. Lastly, I initialized my time to start at 0 and be incremented in steps equating to 0.0333 seconds, since this was the time increment used in my tracker data as well. Here are the results generated by GlowScript. And here's the comparison of my observed results, seen in orange, versus those generated by my computational model, seen in blue. Here's some comparisons. Both sets of data follow a roughly linear trend consistent with constant velocity motion. However, the observed slope is steeper, the observed displacement is greater, the computational model line is perfectly linear, while the observed model line is roughly linear. The two lines do not match, suggesting that the computational model does not match the observed data. So some potential sources of error. The computational model likely assumes ideal conditions, which may not match the real motion, leading to smaller predicted displacements and perfectly linear behavior. We aren't considering motions in directions other than x, which can impact position. And then the marker's odd shape doesn't allow for proper center of mass calculations, which can impact position measurements. Lastly, small forces in the real experiment, like uneven surfaces or air currents, could increase speed or introduce fluctuations that weren't captured in the simulation. For my discussion, let's ask ourselves, what if I had flipped the axes? Well, if I had flipped the axes, my position versus time graph would have the same slope, but it would be negative instead of positive, since interchanging the positive and negative x directions will cause the object to appear to move away from the origin in the opposite direction, such as below 0, and this can be seen in the graph to the right. And then for another question, what does it mean? Is it possible to determine the number of forces added together to give 0 net force in the case of this experiment? Based on the graphical analysis, it's not possible to determine the number of forces that sum to 0 net force. The data in graphical analysis shows the object moved with constant velocity. This indicates that the object had no acceleration and 0 net force. But we cannot determine the number of forces involved that led to 0 net force. Thank you.